Well, Brent put a picture on the screen. Most of you see that. That is an engine. Ffowcs F-18. And Brent is very proud of the picture. And we had this program. I'm going to give a minute introduction for this one. Admiral Cohen came into Tallahassee to see a football game because Florida State is known for football. And we generally bring important people to see football on our campus. And Vice President for Research said, well, there's a guy there, you need to go, he was, I don't know what the conversation was. He said, we need to go see this man. So he was in my lab, and I didn't know what, previous to that, there were some conversations I was hearing about the F-18 noise and all that. And he came to the lab, I was showing around. I've been playing with jet noise. Jet noise wasn't the main forte in my lab until 1999 or so. I've been doing other things. And he came and said, we have a problem on the F-18, and I told him I heard about it, but I said it's a very difficult problem to solve. And I said there are very important people who have worked on this, and not much progress has been made. And in fact, Professor Seiner, who's going to be talking about it, has spent almost 20, 25 years full-time on this problem with enormous amount of money. NASA spent close to $250 million with the industry together trying to address the problem of the high-speed jet noise. So I knew a bit about it and said, it's a very, very difficult problem to solve. He said, no, I'm not asking you to solve. I'm asking you to attempt to solve the problem. Then I said, well, I can't give an answer. I'll talk to you next week. And I called Shon next morning. It was Saturday, I remember. And I called him at Cambridge and said, Shon, this guy was in my office. And this is what he was saying. What do you think I should do? And it's a very difficult problem. You know all about it. And I don't know whether I should embark on this problem. And Shon, first question he asked is how long he's going to be at the ONR. That's the first question he asked. I think this man is going to be there. He just came on board. He'll be there about 2-3 years. Then he said, if anybody can have a crack at it, why don't you do it? Try it. And if you wouldn't have said that second sentence, I would have never attempted to take on this problem because it's an extremely difficult problem. And then when he asked 2 pages, then I said to myself, there is a tremendous amount of experience at NASA Langley over the years on this problem. Then I called Jack when he was in Mississippi, and I said, Jack, I think these people have a problem, and I think we should team up to solve this F-18 problem. And I must say that I was, although as usual, I'm an optimistic person, but back of my mind, I always think it's a very, very difficult problem to solve. But I must admit that it has been fun. It has been 2.5 years. We went from a concept in the laboratory, which Brent Greska is here, who is a PhD. His sweat and blood is what is in this program is. Built a facility, get the thing running and all that. And Jack and his colleagues, Larry Ukeley is here, who have worked very hard. And in almost 2.5 years, we went from a laboratory concept to a full-scale testing. And I'm not very sure. There is a program in anywhere accelerated that fast. But the demands of Gabriel has been such that it has become an admiral. He said, I don't want you guys to play around with this stuff. I just want you to come up with an idea, do something, and go to the engine, demonstrate to us. And indeed we did. And I must say, which we will find out later on, it has been quite a successful program, at least from an academic point of view. Along the way, students have a lot of fun. That's very important. Along the way, you want to make sure that the graduate students are learning and having a lot of fun in doing that. So that is the session which I think this morning is going to be, and Professor Seiner will share it.
Okay, thank you. All right, so I'm Jack Seiner from the University of Mississippi. And Brent, where is the talk on here?
In the right-hand corner, right-hand side.
Hey, Brent, you want to sit up front and try?
Okay.
Oh, okay, there it is there. Yeah. Well, this is interesting. How come the doesn't drop down? You have too much on your computer. Oh, I'm trying to put it in the slideshow. Oh, this is going to be interesting. Actually, I thought that Luis Lorenko was going to chair this session, and then if I ran over, it would remind me and things like this. So now I have to also do that, I suppose, or someone else will have to do it. So actually, this is the title that was given to me as well. I didn't make that title up. That was something that Yulu had provided. And of course, this is, we're going to be talking to honor Shon Ffowcs. But I should have to say this, is that in the late 90s when I was a graduate student, Shon came to visit me at Penn State. Not me, but to visit people at Penn State, where I had a chance to go over the perspectives of what I was going to do for my PhD dissertation. And I had a chance to go through it with Shon, and that was really a great opportunity for a young student and to get the encouragement from him at the time. And here I spent a while working in this field as a result of perhaps that conversation. Now let's see, does this thing have a, where's the page down?
Spacebar.
Spacebar over
The space form? Okay. This work that I'm going to talk about was funded by ONR, particularly Gabriel Roy. There's a few target goals that this program has. There's a longer range goal, which has more reduction than I've listed up here. But the first one I've listed up here is to reduce this aircraft noise by a factor of half. That has real implications in decisions that are made for replacement of Tomcats and the locations where this would go. If you could reduce it by half, it would be more in line with that type of an aircraft. But after interviews with many of the pilots, it's very, very clear that one must be able to do this with minimum performance impact on the aircraft. So when we were working at NASA, we had all kinds of things that we did. One of them was a program that we worked with the CIA, where we achieved actually 50 dB noise reduction with a 50% thrust penalty. It was okay for the mission that was there, but we couldn't apply anything like that to this program. We had to only choose those things that could be where we could modify the aircraft with minimal modifications, keep the performance up, and then see what kind of noise reduction we got. So the participants I've listed here, the University of Mississippi, Florida State, and a company called Combustion Research and Flow Technology, Craft. We worked together on this program. And this is basically, I'll just mention a few things about, I hope I'm not standing in the way here, what the aircraft conditions were, because we did, both at Florida State and at the University of Mississippi, we were studying 1/10 scale models. And that was important. I don't know if it will come out in this talk or not, but the information that we gathered in the laboratory really held up and provided good guidance on full-scale testing that we were going to do. So we talked about we did a flight test simply to get the conditions to build the models, and we then went and we did the experiments at the Naval Air Weapons Center Aircraft Division in Lakehurst. And then I'll talk a little bit about some of the model results and the full-scale acoustic and IR productions, and then summarize and conclude and all that stuff. Now, so if I use the word SDLP, it stands for Field Carrier Landing Practice. So the flight test determined our model geometry parameters, and all this is up here just to point out that one unfortunate thing we couldn't get in full-scale testing was the 414 engine. That would have been better for us because we would have been able to demonstrate a larger amount of noise reduction. We ended up with a 404, which has much lower pressures and temperatures, and there's only so much noise reduction you can get out of that. But nevertheless, that was our full-scale test. And the 10th-scale model geometry was like this. And we were able to run engine cycle decks and develop parameters for testing on the models. And just to point out that the engines that we're dealing with are extremely low bypass ratio engines. This is why they're so noisy. As you can see, I've listed the bypass ratio there for that engine. Okay, so this is the chart that, this is the mission profile that they run when they fly the aircraft. And these are tabled for the two different types of engines, the 414 and the 404, 400. And so there are specific things that are done, and from those you can extract the parameters that one needs by running the engine cycle deck for the aircraft. And we actually, I'll just point out, over here, is this a pointer?
Yeah.
Oh. Is it in its case? Well, okay. Okay. Press that. Just off to the right here. So this at 90 degrees to the jet axis is a compare. There's three lines that are being compared, three spectra. The black is measured data from the flight test. The green is prediction by ANA, and the red is scaled model data from the laboratory. You can see they group really well. So it shows that we were satisfied that what we measured in the laboratory might actually have some realistic characteristics. Now, these are the experimental facilities. This, in the NCPA, we have an anechoic room, and this is one of the nozzles that is up there. And it allows us to study these tenth scale models, and we can run temperatures of up to 2100 degrees Rankine. What we did is that we constructed hardware. We had a propane swirl can combustor for getting the temperatures, but the nozzle hardware that we constructed, this is a typical engine cut from the center body on out through the convergent and divergent flaps. And what we constructed in the laboratory was model geometry that was very, very similar to the actual engine. The only thing that we didn't do is we didn't put in an augmenter. So that wasn't present in the model testing. This just shows some examples. The things that we did at the NCPA in comparison to Florida State looked at microjet water injection. We were looking at modifications that we can make to the engine nozzle that are practical and something that you could actually accomplish. One of them that was to actually modify the engine outer divergent flaps with chevron-style devices that would project into the flow. And this is how we did this in model scale. And we also studied chevrons that were in the flow that actually were ported, where we could also spray water at the same time to try to get a larger extension without having as much thrust loss. One of the other modifications that we looked at doing was to modify a thing known, I have a better slide that shows you this, but this is in general, where this slide shows where these parts are. And all these engines have seals that cover the divergent flaps on the interior to keep the engine from burning up and also having air flow through the flaps. So the seals, this is a typical cut, and what we did is that we redesigned the seal to look something like this in locations around the engine like that. And in general, the idea is that these seals are based on a method of characteristics design. One thing we want to, there are two things we wanted to do. Getting rid of shock noise is always a nice thing to do, so that was one of the goals of that. And of course, when you do that, we were also looking to increase thrust augmentation through increase of pressure along the inner wall. And that would be one of the characteristics of the design. You get mixing noise enhancement because we were looking at corrugating these seals and generating counter-rotating vorticity, which then should also lead to plume infrared signature reduction. And from the model testing, we found we only needed 6 rather than 12 seals. There are 12 internal seals. We only needed the best configuration, which was 6, and I have a slide showing it. So this is what we did in the model. This shows the 10th scale seal, and this is a solid model assembly of that. The next picture shows the actual model that was constructed constructed and tested in our laboratory. You can see the individual seals here that would be placed into the nozzle. This here is the baseline nozzle insert. At Melcadley, this is a picture of an F404. I've had this picture for a long time, and I was just hoping that it wouldn't be the engine that we ended up with, and it turns out it's something like that. It's a 404 engine. But anyway, it's on their multi-purpose test stand, and it has an ability to measure up to 50,000 pounds of thrust. But what we had to do for this particular test, when you do acoustics at the same time, you have to raise the engine centerline height up so that you don't have really shallow angles, grazing angles to the microphone. So we had to build an extra stand for this and mount their engine on that stand. And then we had to go through some calibration procedure for the balance. This is what the acoustic array looked like. We used every 10 degrees, so there's 19 microphones on this array at 80 diameters, which is far field. And then we had an inner array of microphones at 55 jet diameters, which is equal to what we had at the NCPA when we did bottle testing. And it turns out that this is good. We were able to propagate the waves from here to here with no problem. So even this distance here looks like this is in the far field. This is, I don't think you can see very much here. This is the engine and this is the microphone out on the field, but you can see that the surface is fairly decent for doing these types of tests. This stand that they had is completely, can rotate 360 degrees. So it was very nice to be able to use a facility like this, and Brent will spend time showing and talking about the application of nitrogen. These are nitrogen trailers, and then a water tank that was used to inject water into the engine. All right, this is a schematic solid model of the engine seal. Now it turns out that the engine seals are different than the model seals. And that is because of the thing that there's a difference in what is known as the physical throat, okay, which is a 1D, the 1D version and the physical throat. Because of the boundary layer in a real engine, one has to decide. So the design of the actual seal itself is different in full scale than it is in model. The other thing that we learned when we did this is that we didn't have tremendous access to the engine. And so when we went to do the test, actually what we had to do is we had to trim this part of the corrugated seal because it went clear. And actually I think that did affect some of the acoustic results we obtained. If we had a 414 engine, there's less difficulty in being able to do that than on this engine. All right, this is what it looked like on the stand. You can see this is the 6 corrugated engine seals. This is a typical flat seal that they use currently. And I tried to draw an arrow here. Underneath these seals are the divergent flaps, as you can see here. So that's actually the configuration of it here. They held up very nicely during the test as well. And then this is just a picture. We used chevrons that were attached to the outer divergent flaps. We used 12 here, and then also version of 6, and Brent will talk about the microjet injectors when he talk comes up. All right, now there were numerical simulations done, and one should always do that because one learns whether you have at least the right thought process. Now, of course, I just said that, but now what I have to say is this, and you can almost see it yourself. The calculations, we had 2 different style chevrons, and what you see on the upper part of each figure is the total kinetic energy of the baseline engine or the baseline nozzle, and the lower part is the turbulent kinetic energy of the suppressed configuration, and this actually shows there's no difference. We couldn't pick up any difference in the calculation, although the data shows that there is some difference. So one has to keep that in mind. That may happen. Now, in the case of the corrugated seals, they work very well. What this shows are are line plots of pressure, Mach number, and so on and so forth. And the goal, of course, is to reduce shocks so you can reduce shock noise. And as you can see, the upper part of the figure is the baseline engine without any corrugated seals. This is in the trowel of the corrugation, and this is at the apex of the corrugation. And one can see one has done a reasonable job at reducing shocks in general. They're very weak now. And also at the same time, this is the turbulent kinetic energy. And you can see, at least over the first initial radii of the jet, that there's a good reduction in turbulent kinetic energy. Now the reason that, and I think this may be the next chart, it isn't, but what is this one? This is more of the same thing with the 12 and the 6 seal. So what you see here, I think maybe I'll use the bypass this a little bit because I think the next one can see it a little bit better. And now these are just at various cross planes at 1, 5, 2, and 10. And what you see here is the baseline over here, and then you see when we calculated for 12 corrugated seals, and here we only have 6 corrugated seals. And you can see as you evolve downstream, and perhaps the message is this, by 10 diameters, this is the baseline engine, and the turbulent kinetic energy is very, very high. It's tremendously reduced with 12 corrugated seals, but much, much better with 6. And the reason has to go, if you look back here, the vortices that are induced by the corrugated seals are free to grow and encompass fluid into the engine, but when they're spaced too close together, that gets shut off. So this is why the 6 work better than 12. And we found this in many other instances as well. And this just shows the reductions in turbulent kinetic energy and some trial using Craig Hunter's Jet 3D code at NASA Langley to predict the noise reduction as associated with the corrugated seals. And you can see it does produce a few dB noise reduction. Now, I'll try to go through this. How am I doing on time? Anyone have any? I don't even know when we started. When do we start? When are we supposed to be done with this talk?
5 minutes. 5 minutes.
5 minutes?
That's a long time.
All right. All right, so this is the tabs in the model, and there's about, the second style chevron produced about 2 dB noise reduction, and the CFD predicted about 0.5% thrust loss with that. When we use air-powered or water-powered spray in the ported chevrons, no change, no improvement was made with those. They need to be looked at if one is going to use that. With the corrugated seals, this is 96% power, mil power, 95% power. This is the noise reduction we achieved. You can see here there's a good noise reduction in the forward arc due to the shock noise reduction. And there is about a 4 dB reduction in noise with the corrugated seals. These are just some other power settings. And they're in there to just show that you get noise reduction, actually, at many other of the engine power settings, even subsonically, it doesn't do bad. And the real thing is that shock noise is suppressed everywhere at all engine power settings, which was very, very interesting. And this shows this right here. These are various power settings, and you can see how the shock noise is reduced across the board, and the mixing noise as well. All right, so full-scale results. All right, and as I said, we had some problem. We had to change the design of these because of the difference between one-dimensional work, which would be typical of the model, boundary layers very thin, and a real physical throat. And also we had to cut the entrance to the corrugated seals, which obviously probably diminished their capacity to some degree. But anyway, this shows comparisons between the baseline engine, the 8S seals, and the 6 chevrons. And you can see This is the level of mixing noise reduction. It's only 2 dB, but that's what was observed here. And then this is the reduction in the forward arc, as you can see, compared to the baseline engine. And Brent will talk about the results with the water spray. These are the spectra. I have to admit, I can hardly see this from here, so it must be the light. But there's a green part of the spectrum here, and this blue part of the spectrum, you see tones. That's actually turbine tones. So what we did is that when we reduced the shock noise, the thing that we clearly now see is turbine noise, or turbo machinery noise, in the inlet angle. So we had no plan in this program to reduce that, but of course, you have tremendous opportunity in a military engine to do something about turbo machinery noise if one had some money and some time. So anyway, these are the spectrum levels that shows the characteristics in the forward arc here and in the rear arc and the level of noise reduction that we achieved. And this is a combination of both the seals and the chevrons. The noise reduction is a little greater, but because of the chevron's presence, there is no reduction in shock noise. And these are IR reductions. This is the baseline engine at mill power, and then this is the engine with the 8S corrugated seals. So you can see that the IR is somewhat suppressed. All right, so let me conclude this with this stuff, is that we did a flight test to get the basic parameters. We built model parts, and we were looking at corrugated seals, outer divergent flap chevrons, and microjets were being studied at Florida State. The model corrugated results showed about a 4 dB reduction in the rear arc, and 10 dB reduction in the forward arc because we didn't have turbo machinery noise to contend with. The full-scale results only showed 2, and I think that is due to the actual problem of fitting these corrugated seals into an engine environment. That can be corrected, however, with redesign. And the full-scale chevrons also showed a 2 dB reduction. The calculations showed that the plume shock strength was reduced significantly, which is good. This is why you do these types of calculations. Maximum mixing noise reduction occurred slightly lower than the mill power setting. The aero performance measurement, the highly overexpanded flow that exists in an engine really reduces the utility of using chevrons. And that is actually one of the goals that we had, not just to get rid of shock noise, but to create an environment where we might be able to do effective suppression studies. The boundary layer, or the actual engine itself, has an extremely thick boundary layer, subsonic boundary layer. It's very difficult to get any noise reduction that way. Now, with the corrugated seal design that we have, we've improved it, but there's much more to go. We've made it better, that's why we got the increase in thrust, but there's quite a bit more to be done in the design of that. Some of the future things that we want to do is to conduct model scale experiments with dual potted nacelles with full span model in the Boeing LSAP. And we would like to get an opportunity to evaluate engine performance with these suppression devices. I think that would be very important because we'd actually be able to demonstrate that we can get more noise reduction than we had with the 404 engine, and then perhaps conduct a flight test with the actual F-18. And my final comment is this, is that it was a good program in that we were together between all partners. We were actually able to show how well the model data agreed with full-scale results, which I think is very, very important to have both elements in any program. And what we were able to do, as I've shown you, we were able to reduce noise. We actually were able to enhance aero performance, and we also reduced plume infrared radiation. So those are the three things we wanted to do. So at least what we have done with the corrugated seals is we have a part that's actually very easy to implement onto an engine. On the F414, one tool is used to turn one screw. You slide them out and you put the other ones in. It's that simple. So we have a part that actually allows you to do something like that. With that, I'll stop. Any questions? Yes, that's right, I forgot. Any questions at all? That's correct. So broadband shock noise wouldn't necessarily be an issue at all.
Couldn't you have achieved the same result by simply varying the nozzle exit area?
This does vary the nozzle exit area. It does vary.
But without changing the engine, just changing the scheduling of the exit area.
Oh, you can't do that, no. You have to understand that actually on military engines, the way they're designed, you always are going to have shocks because of their design. You actually have to do something slightly different than that to do that. I mean, they're just straight conic sections. So you're going to have shocks. Even when you set, to give you an example, we did studies with military style engines back at NASA. And the reduction in shock strength is very, very small, even at the design point. I don't know if you know that, but with conical type sections. So you have to do something like this.
They're not designed by method of characteristics. They're just straight sections for manufacturing.
Yeah, that's right. So you can't really do it that way. There's a, yeah?
So in your full-scale model, you had no water injection from your microjets?
Oh, no. Brent is going to get up, and he's going to talk about water injection.
Yes.
The fact that you find that you need 6 of those corrugations to work so well, has it anything to do with the known instabilities of vortex rings?
Yeah, that's part of it. That's part of it. What you need to do is that certainly the vortex that is generated needs to be stable in that period of time. And the period of time is a function of how far downstream you want these vortices pumping. Now, there are some designs that I've done that actually very little is entrained into the plume. It actually entrains early on, but they're very, I've seen these things stable beyond 20 nozzle diameters. That's not what you want to do for noise reduction.
What is the nozzle material you have used there?
What's this question?
Nozzle
I'm sorry.
material.
The nozzle material?
Yes. The seal material and the nozzle material.
All right, the seal material was Inconel. Does that help at all? Is that the question?
Yeah, that's it. Material.
Yeah, that was the material that was used here. Now, that material that could be obviously for flight be manufactured from something else rather than Inconel, but that's what we used because we knew that the temperatures that we were running it at would survive. Okay, well, all right. It might be your last question. What is it?
I was just wondering the differences again between 6 and 12. Do you have some physical insight about whether there's a chance to optimize it even further and get further reduction, changing it from say 6?
Yeah, there's a real possibility of that. Actually, for this particular design, something closer to 5 is what you would want, but from work I've done before. But the problem with that is that you can't just do that because you have a certain number of seals that you're starting with. So you're stuck with picking a number that works out and it's symmetric around.